I'm going to try to explain the Monty Hall problem a bit more intuitively in this video, because it really helped me to think of the events in the way that I did and in the way that I'm going to show you in a second. But this is a problem or a game that befuddles a lot of people, including yours truly. And just so you know, if you didn't get it at first either, you're in great company, because it even took the brilliant mathematician Paul Erdos several days to finally get it. He didn't believe he was wrong at first. So I feel okay about not having gotten it immediately. I mean, not really, because I have an enormous ego, but I think it's good to have dents made in it every now and then. So the game goes like this. This is a reality TV show setup. You are the contestant, and the show is hosted by this guy called Monty. Monty Hall was the host of this TV show, Let's Make a Deal. It was very famous. Americans would watch it. And your prize as the contestant is this car. This is a very cool car. You want this car, trust me. And here are the steps of the game. The car will be hidden behind one of the 3 doors. The other 2 doors will have goats behind them, and you don't want the goats. So step 1 is you pick a door. And then step 2 is that Monty will pick a door. And here's the catch. He will never pick the door with the car. He will always pick a door with a goat. If you've picked the door with the car in your first go, then he'll choose randomly between the other 2 doors. But otherwise, he doesn't have a choice. He always has to pick a door with the goat, which means he knows where the car is. And now step 3 is, should you stay or should you switch to the other door? So suppose you pick door 1. Then Monty goes ahead and he picks door 2, which means this has a goat. And now the question for you is, should you stay with door 1 or should you switch to door 3, which will give you a higher chance of winning, since there are 2 remaining doors and there are 2 remaining objects, this, and these are the 2 doors that are left. It doesn't really matter, and you can either stay or you can move, and you'll have a 50-50 chance of winning or losing with either door, right? Wrong. The actual answer is that moving to door 3 will give you a 2/3 probability of winning, and staying with door 1 will give you a 1/3 probability of winning. It sounds crazy, but the trick here is to recognize that this guy, hang on. Come on. This guy, Monty, he isn't acting randomly. He knows where the car is, and he will never pick that door. So just forget about the numbers for a minute. I'm just going to erase that. Just forget about all the numerical odds for a minute and ask yourself, if you're the contestant and you know that this guy knows where the car is, would you think that he's acting randomly when he picks this door? The answer is no, right? You would go, why didn't Monty pick this door? Is there a car behind it? Is he concealing the car from me by picking this door? And that is the intuition behind this problem. And now we can actually mathematically show that there would be something to your hunch if you thought like that, and that moving to this door increases your probability of winning, and doubles it and makes it 2/3. So in the beginning, we had said that as the contestant, you had picked door 1. And we have 3 possibilities for where the car could be. It could either be behind door 1, behind door 2, or behind door 3. So let's say that C of I is the event that the car is behind door I. Where I is either 1, 2, or 3. Then we have 3 possibilities. We have C1, which is the possibility that the car is behind door 1, we have C2, which is the possibility that car is behind door 2, and then we have C3, which is the possibility that car is behind door 3. And each of these has an equal probability of occurring. So given that we have 3 doors, we have a 1/3 probability of this, 1/3 probability of this, and then 1/3 probability of this. And what we want to calculate is the probability of you winning if you switch, because you're trying to figure out if you should stay with your initial option or if you should switch. So P winning by switching is what you were trying to calculate. So let's move to scenario 1, which is where the car is behind door 1, which was your initial choice. If you switch, you would switch to either door 2 or door 3, but because the car is here behind door 1, your probability of winning by switching here would become 0. The second scenario is that the car is behind door 2, and you had already picked door 1, which meant that Monty would have had to pick door 3 because he's never going to pick the car. He's never going to pick the door with the car behind it because he's obliged to only ever reveal the goat. So if you end up switching, you'll switch to 2, which is the winning door, which makes your probability of winning by switching equal to 1 in this scenario. And then similarly with the scenario that the car is behind door 3. So, yeah. Because Monty can only ever pick the door with the goat, you know that there is no car behind it, and if you end up switching, you will switch to door 3, which is again the winning door, and the probability of you winning by switching, if you switch from door 1 to door 3 and the car is behind door 3, is also 1. And so now we're just going to calculate our total probability of winning by switching, which is which would be you multiply the probability for winning by switching for each scenario by the probability of that scenario itself. So here it would be 0 into 1 by 3 equals 0. 1 times 1 by 3 equals 1 by 3. And 1 times 1 by 3 also equal to 1 by 3. And if you sum that up, you will get 2/3, which means that no matter what door you pick in the beginning, your probability of winning just by switching to the other door becomes 2 by 3. Now, what we've calculated here is the unconditional probability of you winning just by switching, no matter what door you pick in the beginning. We've considered all scenarios, no matter what scenario it is. You increase your chances of winning from 1/3 to 2/3 just by switching doors. What I'm a little bit more interested in, though, is the conditional probability of you winning with this strategy, conditioned on the door that Monty picks. We're going to try to condition our probability of winning by switching on the door that Monty picks. And so for that, I've got 2 possibilities. That's Monty either picks door 2 or door 3, with the event that Monty picks some door j being m of j. So our possibilities become that Monty picks door 2, Monty picks door 3. And we're going to use the law of total probability for this. And we already know that the total probability of winning by using the switch strategy is 2/3. And from the law of total probability, given that we're conditioning on M2 and M3, we know that the probability, this total probability, would be equal to the probability of winning given M2, that's our first scenario, times the probability of M2 happening in the first place, plus the probability of winning by switching, given that Monty has picked door 3, times the probability of Monty picking door 3 in the first place. Now, from our perspective, the goat could be behind either of these remaining doors, door 2 or door 3. And so the probability of Monty picking either door 2 or door 3 is the same, because the show's producers don't care where the goat ends up as long as Monty knows where it is. So suppose the producers put the goat behind door 2, so Monty would pick door 2. If they put it behind door 3, he would pick door 3. He doesn't care, they don't care. And so from our perspective, the probability of Monty picking either door 2 or door 3 is the same, which is a half. And now that we know that, we can also say that the probability of winning if you switch in this scenario of M2 would be equal to the probability of winning if you switch in M3, because if these two are the same, then these two become the same, just in how you calculate a conditional probability. And so we're going to say that the probability of winning if you switch given M2 will be X, and the probability of winning if you switch given M3 will also be X. And now we can plug in what we know. So we know that on the left-hand side, we have the total probability of winning by switching, which is 2/3, which is equal to, and now we have the right-hand side, which is the probability of winning if you switch given M2, which we know is X, times the probability of Monty picking door 2 or M2 in the first place, so that's a half, plus the probability of winning if you switch given M3, which we also know is X, and times the probability of M3 in the first place, so that's also a half, which makes it 2 halves make X equals 2/3. And because we defined X as the probability of winning by switching given either M2 or M3, we know that that is 2/3. So now we can see that whether Monty picks door 2 or door 3, our probability of winning just by switching remains the same, which is our unconditional probability of winning by switching, which was 2/3. And this is a thing that would always trip me up about this problem, which is that this is equivalent to this as well as this. And if you notice, by the mathematical definition of independence, this might suggest at first that the probability of winning by switching is just completely independent of which door Monty picks. So this actually gets to the heart of what is so confusing about the Monty Hall problem, because it looks like the total probability of me winning by switching, which is equal to 2/3, and the probability of me winning by switching given that Monty has picked door 2, which is equal to the probability of me winning by... When did I become the contestant? You were the contestant. So you winning by switching given that Monty has picked door 3, is also equal to 2/3. If both of these are equal to 2/3, they're the same. So it looks like this and this aren't really affecting my total probability of your total probability of winning by switching. When I say my total probability, I mean like my mathematical probability, the stuff that I'm working with. And in the standard definition of the independence of events, we say that if A and B both have probabilities greater than 0, then the two events are independent, if the occurrence of one does not affect the occurrence of another. So by that, I mean that if A and B are two separate events, and the probability of A is not affected by B occurring, then I would say that A is independent of B. And that's what it looks like is happening here, that the probability of me winning by switching is not being affected by the probability of Monty picking door 2 or door 3. So the question then becomes, is this independent of which door Monty picks? And that is probably the most confusing part of this problem, because this is what trips us up in the beginning, when we think that our chances of winning are independent of the door that Monty has picked, and that leads us to a half-half solution. But we know that they're somehow related, so why am I mathematically getting 2/3 and 2/3 for both? So once again, the problem lies with the way that we have framed our events. So it is true that the probability of you winning by switching doesn't really depend on which door Monty has picked. However, that is not the same as saying that the probability of there being a car behind either door 2 or door 3, given that Monty has picked the other door, is still the same. And by that, I mean this. So let's go back to our first scenario where you have picked door 1, Monty has picked door 2 with the goat. And we're trying to figure out what the probability of winning is by switching here or here. Now, suppose that the car is behind door 3, and you switch to door 3, then you will win. However, what the probability of winning by switching does not take into account is that you are only switching to door 3 because door 2 has been picked by Monty. So in other words, Monty is making a decision that is then driving what decision that you are making by when you switch. So for example, for a second, if you know what, let me just make myself the contestant right now, because I'm about to say some mean things. If I were stupid enough to move from door 1 to door 2 after Monty had picked this door and shown me that there is a goat there, had I still switched and moved to door 2, then the probability of me winning by switching would become 0. So in other words, when we are talking about the probability of winning by switching, we're talking about the probability of winning by switching to the door that is not the door that Monty has picked. In other words, there's not much to be gained when we are just looking at the probability of me winning by switching in terms of whether or not the two events, winning by switching and which door Monty picks, are independent. What you want to be asking is there a greater probability of the car being behind door 3, which was our initial C1, C2, and C3 scenario. Let me just make this a little bit cleaner. Okay, so you remember our initial scenario where we had said that each door has an equal probability of having the car behind it. So this was 1/3, this was 1/3, and this was 1/3, and you had picked door 1. However, once Monty picks door 2, then the probability of you winning if you just switch to door 3 becomes 2/3, right? We already calculated this before. So what's really changing here when you say the probability of you winning by switching is the probability that there is a car behind door 3. So what's changing is this probability, which is going from 1/3 to 2/3, which makes the probability of you winning by switching to door 3 also 2/3 because you're picking door 3. We can verify this using the Bayes rule, which is that we can check what the probability is of there being a car behind door 3, given that Monty has picked door 2, which, as we said, as we said, went from 1/3 to 2/3. And so let me put this, you, me, whatever, whoever the contestant is right now, back to door 1. And let's remember that the probability of Monty picking door 2 was just equal to 1 by 2, or a half, because it doesn't matter if you've picked door 1, he's going to pick either door 2 or door 3 from our perspective with equal probability. And then the probability, as we know, of there being a car behind door 3 was initially 1/3. So that is the probability of, that is P of C3. And now we can use the Bayes rule. So we want to know what the probability is of there being a car behind door 3, given that Monty has picked door 2, which is equivalent, from the Bayes rule, of the reverse conditional, which is the probability of Monty picking door 2, given that there's a car behind door 3, times the probability of there being a car behind door 3, all over the probability of Monty picking door 2 in the first place. And now, so for this, if you've picked door 1, and Monty knows that, let me use the pointer. You've picked door 1. Monty knows that there is a car behind door 3, right? What is the probability that he will pick door 2? Well, that's just 1, because if the car is behind door 3, he's never, ever going to pick door 3. And so the probability of him choosing door 2 becomes 1. It would be the same if the car were behind door 2. He would never, ever pick door 2. And so the probability of him picking door 2, given that the car was behind door 2, would be 0. And then the probability of him picking door 3, given that the car was behind door 2, would be 1. So it's either 0 or 1 because it's just an exclusive choice for him. So this thing, that's equal to 1. So if we substitute everything, we can see that this is 1 into the OG probability of there being a car behind door 3, which is 1/3 over 1, 2, which is equal to 1/3 over a half, which then becomes equivalent to 2/3. So now you can see that the probability of there being a car behind door 3 is changing from 1/3, which it was initially over here, to 2/3, now that we know that Monty has picked door 2. And so now you can see, you guys, that what's really changing is the probability of the prize car being behind door 3, because it goes from 1/3 and it just doubles to 2/3. So yes, it's true that the probability of winning by switching is not affected by the door that Monty picks, but the door that Monty picks, that is dependent on the location of the car, and whether or not you win by switching, that's also dependent on the location of the car. So the two events are related, and it's just about how you frame the problem, and how you can create a sequence of events such that you can see what the related events are, even if it seems like the relevant events are not related. You'll find that if you go a little bit further back in the sequence, that they are. And that is why, if you're playing this game and you don't know where the car is, it's kind of in your interest to just switch.